Good day to everyone and Dr. Lincoln Choi. My name is Shasha Azmira and I am presenting our group Nur Hafiza and Muhammad Anwar Shahmi to present the video 2 of our assignment. This flowchart illustrates the investigation flow of our R2-based petrol station system. First, the petrol pump boards generate signal whenever fuel is dispensed. These signals are received by the central controller and trigger a GPIO extended interrupt. The interrupt is then handled by the interrupt service routine, which releases a binary semaphore to wake up the corresponding pump task. This table summarizes the task configuration used in our RTOS implementation. Each task is assigned a specific priority function and stack allocation based on its responsibility. For pump tasks are configured with high priority because they handle real-time fuel pulse detection. This flowchart shows the interrupt handling process in our R2 system. The process starts when a fuel pump generates a pulse during fuel dispensing. This pulse is detected by the SD hardware, which immediately creates an interrupt request. This code shows the implementation of the HAL GPIO SD callback function, which is automatically executed whenever an external interrupt occurs. At the beginning of the function, the interrupt start time is recorded using the CPU cycle counter, and the interrupt counter is incremented for performance monitoring. Next, the program checks which GPIO pin generated the interrupt. If the interrupt comes from pump 1, pump 2, pump 3, or pump 4, the corresponding binary semaphore is released using add semaphore key from ISR. This wakes up the appropriate pump task immediately without performing lengthy processing inside the interrupt service routine. This figure shows the runtime monitoring of our R2 system using the live expiration feature in STM32Cube IDE. Instead of stopping the program, live expressions allow us to observe important variables while the system is running. For example, petrol tank displays the remaining fuel level after dispensing, while ISR count records the number of external interrupts triggered by the fuel pumps. ISR cycles measures the execution time of the interrupt service using the processor cycle counter. In addition, telemetry count keeps track of the telemetry messages that have been processed, and telemetry loop count indicates that telemetry task is continuously executing in the background. This slide demonstrates how our RTOS implementation uses an event-driven approach to improve system efficiency. Unlike traditional polling, where the processor continuously checks for new events, our system only executes a task when an actual event occurs. As shown in the first code snippet, once a pump task successfully receives a semaphore, it simply updates the shared fuel tank using a mid-text to prevent data conflicts. After that, the task sends an event to the telemetry key using OS message put. The code snippet represents the telemetry task. This task remains in the block state while waiting for new messages from the queue. When a pump task sends an event, the telemetry task automatically changes to the ready state, allowing the R2 scheduler to execute it immediately. This slide demonstrates how our R2's implementation uses an event-driven approach to improve system efficiency. As shown in the first code snippet, once a pump task successfully receives a semaphore, it simply updates the shared fuel tank using the mid-text to prevent data conflicts. This task remains in the block state while waiting for new messages from the queue. When the pump task sends an event, the telemetry task automatically changes to the ready state, allowing the R2 scheduler to execute it immediately. This slide demonstrates how mutual exclusion is implemented in our R2 system to protect shared resources. Since all pump tasks update the same petrol tank variable, simultaneous access could result in inconsistent calculation. So to prevent this issue, we use a mid-text named tank mid-text. Before modifying the petrol tank value, a pump task must first acquire the mid-text using OS method weights. While the mid-text is locked, no other task can access the shared variable. After the update is completed, the task immediately releases the mid-text using OS mid-text release, allowing the next waiting task to continue.